Okay, good morning to all of you. Today we are going to discuss about the second part of Debye's model of lattice heat capacity. In our first part, we have been discussed up to this much. That means the number of possible modes of vibration Z mu d mu in frequency range mu and mu plus d mu will be this much. This much we have been discussed in our last class, so I suggest all of you that you go for the last video before you have to watch this video. So next we have to discuss the Debye approximation. So by considering the Debye approximation, we are going to be found at the end that the CV will be related with TQ law. That means Debye TQ law we are going to be found at last. So what are the assumptions and how we are going to derive all the things I have done the note, and we have to follow that one. Okay, so precisely I written those things, whatever in the book I have just written in the note, you just watch it. So Debye approximation. Previously we found the number of possible mode of vibration, that is Z mu d mu in the frequency range mu and mu plus d mu. We found that value is nothing but this much, 4 pi v 2 by CTQ plus 1 by CLQ mu square d mu. That this much we already found in our last class. Okay, so now total number of vibration in a crystal, if we are going to be consider, it can be obtained by integrating Z mu d mu. This, when it will be integrated, then we can get the total number of vibration modes within the proper limit. The lower limit we have to take at the 0, mu equal to 0. The upper limit will be defined by considering the condition that total number of vibration cannot exceed the 3n. So here, whenever we have to integrate this one from 0 to a proper value of frequency, then we can get the number of possible modes of vibration. So what will the upper limit? The upper limit is going to be decided that, or has to be follow the condition that the total number of vibration is not going to be exceed 3n. Why? Suppose we are going to consider the each atom vibration. Each atom vibration means one atom having the 3 degrees of freedom vibration, and if n atom, then 3n number of vibrational modes. So this is the maximum number of vibrational modes. So we have to choose in such a way that the upper limit, whenever we are doing the integration, the total number should not be exceed the 3n. This is the condition that we have to be accept to find out the upper limit. Okay, so these are the explanation I have written, because each atom vibrates with the 3 degree of freedom. So if n atoms present in the crystal, the maximum vibration will be possible 3n. So whatever the upper limit we are going to be consider, and the result should not be greater than 3n. Okay, so that condition we have to follow. Let mu d, this is the mu d be the upper limit, so that the relation satisfied as 0 to mu d, Z mu d mu should have to be less than or equal to, here I written equal to 3n. Let it is equation number 11, because last expression was equation number 10. This is our equation number 10, and from equation number 11 here we starts. So here mu d is called the Debye cutoff frequency. So here 0 to mu d, Z mu d mu, it can be written as Z mu d mu value we found in equation number 10. You can check your note, that is the value of this one. You can just write from equation 10. Okay, from equation number 10, this should have to, I just substituted the value of Z mu d mu over here, d mu equal to 3n, and this will be 3n 0 to mu d, and by integrating we can get mu dq. This is 4 pi v 2 by ct square plus 1 by cl square into mu dq by 3 is equal to 3n. So hence mu dq equal to 9n by 4v into this much. This is equation number 12. Okay, so this is our maximum frequency that we are going to be consider for a crystal. This is the maximum frequency. Above that it should not be accepted. Above that the vibrational number of vibrational mode will be exceed the value of exceed the number 3n. So we have to be inside the frequency limit in which we can get the maximum value of the number of vibrational mode. Maximum will be 3n, should not be exceed the 3n. So the cutoff frequency or the so called Debye cutoff frequency of a solid will be the so called mu d, and this mu d, whenever we are going to consider the mu d, will be this one, and by considering n by v a particular value, suppose we are going to consider a material of n by v is 10 to the 28 per meter square, and the velocity we are going to consider 100 meter square, then we can found the mu d value is approximately this one, or the lambda m, corresponding lambda m. Mu is equal to mu d by lambda m. Okay, and corresponding wavelength is equal to around this much. Means from the wavelength itself it can be predict that the wave having the wavelength is approximately the interatomic distance. So the interatomic distance will be a wavelength which could not be that much acceptable if we are going to consider this Debye concept. So this is one of the drawback for the Debye concept, because this assumption if we are going to consider, then Debye model is not going to satisfy on the base of the continuity, on the base of the continuum of the material. Okay, so this much portion no need to write in the exam. We have to direct calculate our aim to find out the CV. So only for that, this is the explanation that how this is not valid for the higher frequency. Because see, for this is for this much frequency, if it is that the wavelength is approximately interatomic distance, then higher frequency again the wavelength is going to be reduced. So it will not acceptable that the medium is continuum if we are going to consider the so called Debye model like this. Now our aim is that to find out the CB, the specific heat capacity. Now the vibrational energy, total mode of vibration we found. Total mode of vibration is this much. So total energy we are going to find out, and then we have to consider the rate of change of energy with respect to temperature to finding the CP. So the vibrational energy of the crystal is determined by using Planck's law, Planck's theory. The average energy of an oscillator we know by according to Planck's theory, having the frequency mu at the temperature T is given by E average. E average is equal to h mu by e to the h mu by kBt minus 1. Here kB we know that the Boltzmann constant. As we have considered each harmonic oscillator having the same energy, so here the total energy, the vibrational energy of the crystal, this is the average energy of one oscillation or one mode of oscillation. We have this much mode of oscillation, so total number of or total energy will be one average oscillation into total number of mode of oscillation and integration over 0 to mu d. So here 0 to mu d, z mu d mu, and this value is nothing but this much we have been substituted over here. Let it is equation number 13, and here 0 to mu d, and here this value we know that 4 pi v. You just check the equation number 10, whatever you have, equation number 10 previously. 4 pi v 2 by CTQ plus 1 by CLQ mu square d mu. Okay, this is the this expression, this much expression we found from equation number 10. Okay, here I substituted the value of z mu d mu from equation number 10 is this much, and this value is written as such. And now the specific heat capacity is how much? Specific heat capacity is rate of change of total energy with respect to temperature at constant volume. Okay, so this is 0 to mu d. We are going to be take the differentiation of this one. First, where is the function of t? This is the function of t only. Here, exponent of this one. Carefully you have to watch. I am going to explain the differentiation. So this is the constant. There is no function of temperature. So 4 pi v 2 by CTQ plus 1 by CLQ mu square d mu into h mu. Gone. Now this is in the form of 1 by exponent of h mu kBt minus 1. I am going to be differentiate this much with respect to the temperature. So it will be first minus 1 by this much square exponent of h mu by kBt minus 1 square. Gone. Then the derivative of this one, it will be h mu by kb into exponent of h mu by kBt. Again 1 by t we have to take the derivative into minus 1 by t square, right? So it will be 0 to mu d 4 pi v, this much as such I have been written up to this much as such I have been written. Okay, here exponent of h mu by kBt, here you can see h mu by kb, another h mu here is there. So h mu square, kb is here, kb, here you can see t square, so t square, here minus, here another minus plus, whole divided by exponent of h mu by kBt minus 1 square. Okay, now here you can see kb into 0 to mu d 4 pi v into this much as such I have been written up to this much, same terms. So here you can see that here kb is there, 1 kb I multiplied, 1 kb I divided, so it will be kb square. So I can write h mu by kBt into square. Here you have to always remember that b is in subscript. Okay, don't write k into b, this is wrong. Always k subscript of b. Okay, this is nothing but Boltzmann constant. Okay, now come to the next page. For easy explanation I written this line once again in the next page, this one. Okay, now here we are going to consider h mu by kBt equal to x. Okay, see here in the book you can see that directly in the book it has been substituted all the things and written the last formula or last expression, equation number 14, but I just elaborated these substitutions. Here you just watch it. See, here we considered h mu by kBt equal to x and h mu d by kBt equal to xm. Let it is equation number 13i, this is 13ii. So here mu equal to x kBt by h, so d mu equal to kBt by h into dx. Let it is equation number 13 third I. From equation number 12 what we got, this much we got, this is our equation number 12. Okay, this is our equation number 12, this much we got, this much. Okay, this is in inverse, so I can write 1 by this much, so 4 pi v into this much, so 4 pi v into this much will be equal to 9n by mu dq. Okay, so now here you can see mu d will be how much, xm into kBt by h. So here you can put that xm into kBt by h whole cube, because this is mu d cube. Okay, so here 9n into this h cube can be moved to the numerator h cube and divided by xm cube kBt cube. Let it is equation number 13iv, 13iv, 13i, 13ii, 13 third I, 13iv. Okay, now I am just substituting the values. See, kb is there, kb is already here, you can see kb, I have written kb 0 to xm here, yes. See here vd, sorry, here mu d is the upper limit, So mu d is a function of xm, so it will be 0 to xm. So the upper limit will be 0 to xm, and here you can found that 4 pi v this much value is nothing but how much, this much. Just substitute over here 9 n h q by xm q into kbt whole cube, okay, into mu square will be how much, x kbt by h whole square, kbt x by h whole square into d mu value is how much, this much, kbt by h into dx into here we have been considered that h mu by kbt is x, so exponent to the power x exponent to the power x minus 1 whole square into x square, okay. Here you can see that kbt cube, here kbt square, here kbt, so kbt cube got cancelled, here hq, here h square and h in the denominator also h cube got cancelled. We can found 9n kb into 9n 0 to xm 1 by xm cube into x to the power 4. Here one x square will be remaining, we can get x square, here x square, x4 e to the power x dx whole divided by e to the x minus 1 whole square, okay. So now Cv will be equal to, systematically if we are going to write, then 9 n kb 1 by xm cube 0 to xm x to the power 4 into e to the power x into dx whole divided by e to the x minus 1 whole square. Let it is equation number 14. Here let us consider theta subscript d. Theta subscript d is your Debye temperature. So and this value has been considered as h mu d by kb. See here h mu d by kb, this much have been considered as Debye temperature theta d, okay. If so, then xm will be how much, see this is theta d, so xm will be theta d by t, so xm equal to theta d by t. Now Cv can be written as 9 n kb. In case of xm we can write theta d by t, so it will be the t will be moved to the numerator, t by theta d to the power whole cube, and 0 to here xm can be written as theta d by t e to the x into whatever the terms I have been written as such. Let it is equation number 16. So e to the x to the 4 e to the x to the 4 divided by e to the x minus 1 whole square e to the x minus 1 whole square. Let it is equation number 16. Now we have to move for the next page. This is the example of silver that which follows the TQ law or Debye law. This figure you can draw also at the end of the discussion, no problem. First we have to consider the high temperature, how it is behaves. It is obeying the Einstein classical law or not, we have to check, okay. So from equation number 13 means this one. From equation number 13 we have this much, right, that is 0 to mu d z mu h mu by exponent of h mu by kbt minus 1 will be equal to this much, Let it is equation number 18. How we are going to get? You just to do it in your rough by considering 13i, 13ii, 13 third I, 13 IV. That means if you are going to be consider this and these expressions, and you are going to be substitute for all the values over here, then you can found this much value. Here I have been written directly, you can check it in your rough, is equal to how much we found, 9n kbt by h mu d whole cube kbt 0 to xm x cube dx whole divided e to the x minus 1. Let it is equation number 18 by considering these 4 equations whatever we got. So for the high temperature, e to the x minus 1 will be equal to x, because we know that e to the x is equal to 1 plus x square by 2 factorial x cube by 3 factorial and so on. Here minus 1 1 got cancel, and we know that x is nothing but h mu by kBt. So if temperature will be increased, this value will be decreased, so x also is going to be decreased. So for the higher value of x is not going to be considered, only x has to be considered. So e to the x minus 1 will be considered as, or you can approximately equal to x for the high temperature. Okay, so now e will be how much? See, 9n kBt by, see here kBt is there. Here you can see kBt by h mu d is nothing but 1 by xm square. See, here we have been considered that xm is equal to h mu d by kBt. Okay, so from the equation number 13 II, this can be written as 1 by xm cube, right? 0 to xm can be written as theta d by t. Already we have been written here, theta d by t x square dx. Okay, x square dx, because e to the x minus 1 will be x cube, so x square dx. So by integrating this one, we can found here see xm also we found how much? Theta d by t. If we have to put instead of xm theta d by t, it will be t by theta d whole cube, and 0 to theta d by t x cube dx will be equal to 3n kBt. Okay, let it is equation number 19, and Cv will be equal to del E by del T. We can found 3n kb, equation number 20. Suppose we are going to consider n equal to Na, means Avogadro numbers, then it will be 3r, which is exactly matched with our classical and Einstein theory. So it will obey the classical and Einstein theory whenever we consider the high temperature. You can see above theta d, this is the silver, example of silver, above theta d, approximately this is the 225 Kelvin for silver. Above this temperature, this value matched to the 6. You can write 1, 2, 3, 4, 5, 6. This along y-axis we have been taken as Cv. So along x-axis we have taken as temperature. So at the high temperature, that means above theta d, the silver obey the classical as well as Einstein as well as the Debye model. Now we are going to consider the low temperature case. At the low temperature, that means theta is less than that of the theta d. This is our cutoff. This is our theta d. Is your Debye cutoff temperature. Below that temperature, the system has to be obey the TQ law. Is it so or not? Check it. So whenever we are going to consider t less than that of the theta d, then the upper limit of the integration will be infinite for equation number 16. You just consider that equation number 16. This is our equation number 16. Now, if theta d is less than that of the is t, here t is less than that of the theta d, you just consider something by some constant by t is considered towards to 0 Kelvin, so it will be infinite. So theta d by t, when t is very less, is going to be tends to 0, then this value is going to be infinite. So equation number 16 will be written as 9n kb t by theta d whole cube 0 to infinity e to the x to the power 4 dx divided e to the x minus 1 whole square will be equal to 4 by 5. This integration by gamma function, using gamma function we can found 4 by 15 pi to the 4. At last we found 12 by 5 pi to the power 4 n kb into t by theta d whole cube. This is equation number 21. Here Cv is proportional to TQ. So in this equation is well known Debye TQ law and good agreement with experimental data for many substances. A example for silver is shown in the figure. One of the example here, you can see that at the lower temperature, this increasing this increase value of CV is follows the TQ, which is verified by the Debye model, whatever not solved in classical and Einstein model. So thank you very much to watching this video. You pause the video, write down the note properly. If you faced any doubt, you ask me, we are going to discuss. Okay, so thank you.